So now, solving the Schrodinger equation. So solving the Schrodinger equation is no easy task. We will spend half the semester solving the various forms of the Schrodinger equation. Okay? So I'm just going to rewrite that Schrodinger equation that I had up here before. I'm going to write negative h bar squared over 2m, second derivative of psi x with respect to x, potential energy, okay, operating on psi x equals E psi x. And for now, I'm going to assume my potential energy operator is just equal to some constant value. Okay, so we're just going to say constant potential. And I'm going to use the letter V to represent that constant potential. Okay, so now the way that I solve this Schrodinger equation, I have to isolate psi. And I can only isolate psi if an operation allows me to do so. For example, I'm going to first put here, I'm going to try to write this clearly and slow down, second derivative of psi x. So I can't like divide out that second derivative. I have to actually do the second derivative, okay? But I can certainly divide out the negative h bar squared divided by 2m because that's just multiplying by a constant, all right? And so I'm going to say that is now equal to, let's see here. I'm going to flip it because if I wanted to isolate that, I can cancel that. Negative 2m over h bar squared, okay? And now continuing along with this here, we know that E is going to be a constant, and here we've defined V as a constant. So that also means I can separate that operation from psi, okay, through algebraic manipulation. And so I'm going to do a couple steps at once, and I'll just describe what I'm doing. I'm going to subtract the V psi over to that side, and then collect like terms. And that gives me E minus V times psi x, okay? And so you might be thinking, well, how? You were just telling us we have to do this operation and all that other stuff. Well, look, we're still carrying out all those operations on psi, right? Now, the way that this operation is going to go, it's negative 2m divided by h bar squared times the quantity E minus V operates on psi x. Of course, we would only get that after we take the second derivative of psi x, okay? And so as it turns out, this is what I'm going to call, I'm going to change color here to make it stand out. So this is a standard second order Diffie Q. So where Diffie Q is my little abbreviation for a differential equation, okay? Differential equation. And second order meaning the second derivative. So a first order differential equation would be the first derivative. A third order differential equation would be the third derivative, okay? And so as it turns out, because this is a fairly simple form of this equation, and the simplest form of this equation, I'll give it to you generically. So this is d dx of the function f of x equals some constant c times f of x. So that's our standard second order differential equation. And as it turns out, there is a solution to the standard second order differential equation, okay? And that solution goes as the following. So I'm going to write, here we go, I'll write this, solve. We don't know how to do that yet, but I am going to teach you how to solve second order differential equations, okay? So it turns out the solution to this thing here, okay, is psi of x equals cosine times kx, where k is a constant, and that constant equals 2 times m times e minus v, all divided by h bar squared, all square root. Okay? So I'll also remind you that in general, when I have this function, cosine kx, this is a standard function of a wave. Okay, so this is a wave with wavelength lambda 2 pi divided by k. So in other words, k is what we call the wave number. Okay? Very cool stuff. Did I leave myself enough room here? I did not leave myself enough room to do the next thing that I want to show. So let's see here. Okay, that's fine. I'm going to go over to the Mathematica now because I want to remind you, I want to show you the connection between this wave number and the wave numbers that we were just talking about in my review lecture. Okay? So if I now define a function, I'm going to say, I'm going to just plot it straight off the bat. Plot cosine kx bracket. And we're going to go from x from, let's say, 0 to 2 pi. End bracket. And I think that's enough to give me a lovely cosine function. Oh, I have to supply a value for k, of course. So what we're going to do is now say manipulate, bracket, comma, and then now we're going to let k go from, let's make it go from 0.1 to 1. End bracket. Lovely. Okay, there is my cosine function. And now I've got 0.1, and I'm going to go in here and put 1.0 for k. So now I've just got, let's see here, where are we at? Yes, so I've just got a cosine graph, right? A simple cosine graph where my wave number is equal to 1. So I'll remind you, because the wave number, right, is, look, right here, wave number is 1 over wavelength, and we do have that factor of 2 pi in there. So that's 2 pi divided by lambda, all right? A smaller wave number, small wave number, gives me a big wavelength, okay? So let's see how that shakes out here. Oh, you know what I wanted to do? Apologies. I wanted to make this scale all the way up to 10, not to 1. So let's go back to that. Let's go to my, 1.0. And you can probably already see where I'm kind of getting at here, right? So we said a small wave number is a big wavelength. And so now let's look what happens to the wavelength as I make k smaller. Look at that. The wavelength is getting bigger. And so what that also means, the energy is getting smaller. Okay, so small wave number, big wavelength, small energy. On the opposite hand, all right, a large wave number is a small wavelength, which is a big energy. And if I scale now my wave number up larger, you can see I'm getting smaller and smaller wavelengths, which would owe to bigger energies. Okay? And so